yesterday, we went over energy transfers, and we kind of talked about that in terms of a global system. We're going to look at that more in depth. Right now, we're going to be looking at how wind patterns, which are an example of which heat transfer method? Convection. How they are going to help us transfer energy, from one place to another on Earth. So we're going to look at how it's distributed first off. Look at the role the winds play in distributing energy. We're going to talk about something called the Coriolis Effect. And recognize that global wind patterns are a product of both convection, that's the movement of air, due to the changes in temperature or differences in energy, as well as the fact that the Earth rotates underneath its atmosphere. We kind of have this idea that the Earth and the air around it always move together, but they don't. They're not attached. There's nothing holding the atmosphere stuck to the surface of the Earth. So the Earth can actually spin underneath its atmosphere, right? And that can produce some of the prevailing wind patterns that we experience. It's kind of like, if you shouldn't really do this, but if you stuck your head out the window of a moving car, even if it's not a windy day, it feels windy, because you're moving through the air at a high rate of speed, even if the air is perfectly still. Well, there's a bit of that going on when the Earth rotates underneath its atmosphere. Now, the atmosphere generally kind of moves with the Earth, but they don't move together completely. All right. So, the Earth's atmosphere is always moving. It's always in motion due to differences in pressure, due to differences in temperature, and we detect that movement as wind. Now, as well as the atmosphere always moving, the Earth is always rotating, and the Earth rotates in this direction. So the gray arrow here, I'll make it a little more obvious. The Earth's direction of rotation is this way, right? Which is why the sun always rises in the east and sets in the west. As we come into the light, we see it in the east and so on. Everybody follow me there? Now, as we move through, or as we rotate that way, it makes it feel like winds are moving the other way, because we're moving through the air in that direction. So even though the air isn't actually necessarily moving this way, it feels that way. Most of the time, air on Earth is actually moving north-south. But as you know, around here, it feels like most of the time the wind comes from the... Wow, you guys need to be way more observant. It's always from the southwest or west here. That's where our prevailing winds come from, and that's kind of odd, seeing that air is usually moving north-south and up and down. So nature doesn't like imbalance, or inequity. So there's always going to be a movement of air trying to balance, like we said before, differences in energy and differences in pressure. So that creates the movement of air that we sense as wind. And obviously, if you're like on a ship or something like that, you can kind of you can feel that. Anywhere you can feel that. Here you can feel that. We can see flags moving around here, because there's usually some wind. All right. Now, wind transports heat and heat energy, sensible heat, the kind we can feel, as well as moisture. Now, if it's transferring moisture, that moisture holds what kind of heat that we talked about yesterday? Latent heat. So remember that latent heat is still involved in all of this, and wind is going to be moving this water vapor from one place to another, and that water vapor holds all that latent heat as well. Now, the thing we want to talk about right now is a particular wind mechanism known as the jet stream. Now, the jet stream is a high altitude, high velocity wind mechanism. And its shape is always changing. So when the jet stream changes its shape, we generally get a change in our weather patterns. Because the jet stream can push large air masses around, and vice versa. So this would be an extremely unlikely scenario. For the shape of the jet stream, it would very rarely ever look like this. Most of the time, it just kind of goes across. Something like this. It might be a bit serpentine sometimes. I'm going to change the size of my face. So most of the time it just kind of does something like this. okay, and it moves across the continent, and that can influence where certain, you know, big again. Somebody's messing. Okay. All right, so we got the jet stream kind of can, like I said, can change its shape. Now you can see that here it's represented by a purple line in this picture here. So the jet stream has got this odd shape. What's forced it way out over here is all this cold air, okay, that's up here in the Arctic. Okay, this would be kind of like a polar vortex kind of situation where we've got this massive cold air that's moving down. Okay, yet over here it's warm and dry because the jet stream is keeping it over there. Okay. Now, what's going to happen here is because the jet stream is separating two very different types of weather, okay, or air masses, is it's going to produce an area of very unsettled conditions. Okay. If this was a summertime situation, okay, this whole area here would be ripe for what kind of weather? Thunderstorms. In fact, look where this is going. What's this area generally called? Yeah, that's Tornado Alley. Okay. Now you'll also notice that the border between this one and this one right here also happens to be right where we live. Yeah. Okay. That's generally what we see because the mountains have a tendency to influence the location of the jet stream quite a bit. Okay. Which is why, of course, mountain barriers are a factor affecting climate. Okay. They can really influence your weather situations. Okay. Now, if you're a pilot, okay, and you can get up into the jet stream, would you do it? Maybe. Yeah. Depends which way you're flying. Okay? Yeah, if you're going from west to east, you try and catch the jet stream as much as you can. Right? It gives you a little boost. You don't use as much fuel. You arrive at your destination a little bit early. Okay? Everybody's happy. Okay? If you're flying the other way, you want to avoid it entirely because obviously you'd be flying right into this very high-speed wind. Okay? How many people have been on a plane when they've encountered a lot of turbulence? Okay. When you encounter turbulence, you're usually crossing the jet stream. Okay, so you're going through an area of unsettled air, and the pilot will usually change altitude. Okay, it starts to get really, really turbulent. They'll either go up or they'll descend a little bit to try and get out of it, right? Because obviously you don't want to be shaking everybody around inside the plane. It's not good for the plane. Okay, so they try and avoid that as much as they can. But if you're traveling with it, it's just like having a sail. Okay, and it just pushes you along, and it's awesome for that. Okay, but you can see how this high altitude wind would push weather in this direction. You can see this chilly air being pushed by this high pressure area, but as soon as it encounters the jet stream alters its trajectory and forces it out that way. Okay, so the jet stream can really move air masses around and cause these changes in weather, and when those air masses are moving, they take their moisture with them, okay, they take that latent heat along, all of that kind of stuff, and that can really help to transfer energy from one place to another. Right? So that's the role of the jet stream, to move large air masses around and help to transfer energy, okay, in the form of sensible and latent heat. Okay, everybody all right with that idea? Okay, there's always a question about the jet stream. Okay, now prevailing winds. Okay, like we said before, okay, our prevailing winds in this area are typically from the southwest or west. Okay, now what's usually going on is convection. Okay, so at the equator, where obviously they get more sunlight than anywhere else, okay, the air gets warm and warm air rises. So you can see, okay, in this cell right here, okay, we've got warm air moving upwards. Okay, when that warm air moves upwards, it cools a little bit, but this warm air, because it's still in kind of an equatorial area, will move down to replace it. Okay, everyone follow me on that? Okay, so as this hot air rises, this air will move in from the north to replace it. So we've got air that's moving from north to south. Okay, and then this air here, it shows it as blue, but it's still quite warm because it's near the equator, will move northward. It can't fall down, so it moves northward. And as it moves northward, it can actually kind of wedge underneath, okay, this air here. And it'll actually start like a current that moves from south to north. And this is the area that we're in, okay, where winds are typically moving from south to north. Right? And then up here at the poles, you also have a convection current going on. Okay, it's more lateral and just kind of goes like this. Okay, as opposed to up and down, it just kind of rotates clockwise. Okay. Now that's what can cause the polar vortex. Okay? When that polar vortex gets really strong, it will move downwards. Okay? This line here is not a fixed line. This moves down, it moves up, it moves down, it moves up. Okay? When we're going into one of those really, periods of deep cold, okay, then that polar vortex just descends further, okay, and affects us more. All right, so back to the prevailing winds here. So we've got winds moving from the north to the south here near the equator. But as that's going on, the Earth rotates and moves this way underneath that air. Okay, so the Earth is going this way, but the air is moving this way. So what we feel is wind that's coming from not due north, but northeast. Okay, it's trying to move south from the north, and we're moving into it as it does that. So it makes it feel like it's coming at an angle. It really isn't, but it's a combination of essentially two vectors. Okay, a southward vector and an eastward vector. Okay, it makes us feel like the wind's coming out of the northeast, okay, in that area. Right? We call actually those the trade winds. Okay? Back when the only way to get stuff from Europe to North America was by ship. Okay, these were the winds that would be used. Okay, the trade routes essentially had people sailing south, okay, from Europe, okay, until they could get close enough to get these easterly winds, okay, that would take them to the Americas, and then they would sail northwards and go up the coast and drop off their goods, and then they would catch these winds that would push them back, okay, to Europe. You kind of follow me there? That's how kind of that went. But they called these ones the trade winds and these ones the westerlies because they came out of the west. Right? So we live in this area right here, actually kind of right on the edge of the polar easterlies and these westerlies. Most of the time it's westerly, but if we get a northeast wind, what's going to happen? Yeah, it's going to get ugly. Okay? Nothing good weather-wise ever comes from the northeast. Okay? All it can bring is cold. All right, so what we've got then is in our area here, okay, warm air is trying to move from south to north. As the Earth rotates this way, it actually pushes that air in this direction, making it appear as though it comes from the southwest, which is our prevailing wind pattern. Okay, but like we say, because we're right on the border, sometimes we get the easterlies. Most of the time, we get the westerlies. If you lived anywhere, basically in the United States, your prevailing wind pattern would be from the west. Everybody all right with that? Okay, so here's what we need to take away from this slide. Prevailing winds are a combination of convection and the rotation of the Earth. Okay, now there's obviously on Earth 3 different bands of convection. Okay, there's the equatorial band, okay, and then there's the westerly or mid-latitude band, and then there's the polar band. Okay, the polar band and the equatorial band both produce easterly winds because the wind is trying to move from north to south. Okay, and in the mid-latitude band, okay, the wind is trying to, or the air is trying to move from south to north, so it gets deflected the other way. Okay, so prevailing winds are the product of both convection and the rotation of the Earth. All right, so as this is going on, okay, again, like we said, the motion of the Earth deflects these winds. So, okay, here's the equator, right? And so we've got hot air rising, okay, and then cooler air from the north moving in to replace it. The Earth rotates underneath it, deflecting it this way, okay? At this latitude here, our convection current actually works the other way, okay? That equatorial air wedges underneath and moves towards the north, okay, gets deflected, okay, this direction giving us westerly winds, okay, and then at the pole, again, we've got air moving from north to south, so it gets deflected to the east, which creates that vortex at the pole. Okay, so there's always kind of a spinning vortex at either pole. Now, we can't really see that all that well on Earth. Okay, you can kind of watch it if there's cloud cover. You can see that the clouds generally move that way. Okay, you can also, if you've ever watched, like when the Weather Network shows the track of a hurricane. Okay, you ever notice that a hurricane always follows the same track? Okay, it's the same places that always get hit by a hurricane. Right? So the reason for that is hurricanes build down here by the equator where there's energy available to build them. Okay, they blow eastward and then they encounter this area right here, Florida, the place that always gets hit, okay, and all the little Caribbean islands, okay, they all get hit by it, and then as it starts to peter out, it starts to rotate and then get blown back out to sea as it encounters the shore, okay, and it follows that track basically every time, right? Sometimes if a hurricane is strong enough, its effects can even be felt in Canada. Right? There have been times where like Newfoundland has got hit by the tail end of a really, really strong hurricane. All right, does that make sense to everybody? Okay. So like I said, it's hard to see this on Earth because our clouds are not consistent. Sometimes there's cloud cover, sometimes there isn't. When there is cloud cover, you can sometimes see that movement, okay? But it's easier to see if you watch it on something bigger. Okay, you can see this exact same pattern forming and happening on Jupiter because its clouds are always present. Okay, now because Jupiter is much bigger, it has way more bands than Earth does. But you can actually see the winds going in different directions. It almost looks like parts of Jupiter rotate this way, parts of Jupiter rotate this way. That's what it looks like. Okay, actually all of Jupiter rotates the same direction. Okay, but the winds are so strong that you can actually see them going in opposite directions. I have a short clip here that I'll show you of that. Okay, hopefully it works. It does have this really cheesy, like computer voice over dialogue. Okay, so the Coriolis effect is part of this rotation of the Earth effect, okay, that goes on in terms of deflecting winds. When winds are trying to move north-south, because that's the way you move when you're trying to change, when you're trying to balance differences in energy, okay, as the Earth rotates underneath, they get deflected. That's called the Coriolis effect. Okay, so the Coriolis effect is the deflection of an object from a straight line by the rotation of the object underneath. In this case, the Earth. So if the Earth was like just a solid ball, okay, and I rolled, or tried to draw a line down it, okay, and rotated it while I was doing that, I wouldn't be able to draw a straight line, would I? Okay, in fact, I'll show you because I think I have a ball. So the Coriolis effect is responsible for producing patterns of prevailing winds as it deflects convecting air. Okay, so that's basically what we need to get out of that. All right, everybody with me there? Okay, so that's what the Coriolis effect is. Okay, so I would like you guys to answer those questions. I'll give you a couple minutes to answer those questions, then we'll go over them, and then we're going to move on to specific heat capacity. Okay, got a fair amount of stuff to get through today, please. So, the effect of unequal distribution of thermal energy on Earth. What does that cause?
What does it cause?
No, what does it cause? What is the effect of it? Okay, if there's differences in energy and differences in temperature, we're going to get wind because of convection, right? If we have a difference in energy, the second law of thermodynamics says that difference in energy has to be balanced. The way that that'll happen is through convection because the atmosphere is fluid. Okay, so convection will occur, that's wind, okay, we'll feel wind. All right, explain how the Coriolis effect influences the direction of winds in the northern hemisphere. All right, so as the Earth rotates, okay, in the direction that it rotates, and wind is moving, okay, any winds moving from north to south get deflected so that they feel like they're coming from the east. Okay, if they're moving from south to north, they get deflected so they feel like they're coming from the west. Okay, that's basically what I need to explain. All right, trade winds. Trade winds are where? Near the equator. They are easterlies because they come from the east. Okay, they're a north-south moving wind, but because of the movement of the Earth, okay, they feel like they're coming from the east. All right, and really important, jet streams. What are jet streams? Okay, high speed, high altitude winds that influence weather patterns and transfer energy, both sensible and latent heat. Okay, important that that one is included. Okay, questions there? Good with those? Okay, so now we've got to talk about heat capacity. Heat capacity is going to relate to a couple of things that we've already talked about, especially factors affecting climate. Okay, so we'll talk a bit about what heat capacity is, okay, and then there's a tiny bit of math to do with it. It's super easy though, okay? That's the formula. E equals m times c times delta t. Okay? Everything is multiplied. So if I want to manipulate for something else, what do I do with everything else? Divide it to the other side. Super easy formula. Okay? All right. So heat capacity. Okay? The definition of heat capacity is the amount of heat required to raise the temperature of an object by 1 degree Celsius. Okay? That is the object's heat capacity. Okay? We say that for an object because an object could be made of many different materials. Right? If we're talking about specific heat capacity, this is a physical property for each material. Okay, in the same way that solubility is a physical property, okay, and things like that from back in the chemistry unit. Okay, specific heat capacity is a physical property of each material, and it is the amount of heat in joules required to raise the temperature of 1 gram of a specific substance by 1 degree Celsius. Okay, so the amount of energy required to change the temperature of something, okay, 1 gram of something by 1 degree Celsius. Right? So the units for specific heat capacity are joules per gram degree Celsius, because it's the amount of joules needed to heat 1 gram by degree Celsius, joules per gram degree Celsius. Okay, now heat capacity is important in this regard. Okay, remember how we said that being close to an ocean can really affect your climate? Okay, and we said that that was the reason for that was that the ocean can hold on to heat. It can. It can because the heat capacity of water, the specific heat capacity of water, sorry, is 4.2 joules per gram degree Celsius. Okay? That may not seem like a very big number, but trust me, it is. Okay? To raise the temperature of 1 gram of water, that's 1 milliliter. Okay? About the equivalent if you had like a drop of water about the size of a raisin. Okay, that's about 1 gram of water. Okay, it would take 4.2 joules of energy to raise the temperature of that single drop of water by 1 degree Celsius. Okay, so water can hold a lot of energy without changing its temperature. Okay, so if I live in Vancouver or Victoria, I'm going to have a much more temperate climate. Because even though the air temperature might get low, a lot of energy can move from the ocean into the air, and the ocean won't change its temperature very much. But it can change the temperature of the air considerably, because the heat capacity of air is much, much lower. Okay? So in that way, because water doesn't change its temperature very easily, okay, then it can retain a lot of heat and thus influence or regulate or moderate your climate. Right? That sort of makes sense? The warmer the ocean is where you are, the bigger that effect or more noticeable that effect can be. Okay? If you live in Victoria, I mean, the ocean still feels cold there, but it's warmer than the ocean is in Newfoundland. Okay? And so it regulates the temperature in a much different way. All right. Does that sort of make sense to everybody? Okay. On your periodic table, if you still have it, okay, there should be a list of, there's only a few on there. I take it back. But in your workbook package, there is, okay, or in the notes package, one or the other, there's a big long list of specific heat capacities. I think it's in the global systems worksheet package. Yeah, there it is. It's the first page. Okay, so these are some of the specific heat capacities of common substances. So aluminum, okay, has a heat capacity, a specific heat capacity of 0.9 joules per gram degree Celsius. Okay, that means water can absorb 4 times as much energy, a little more than 4 times as much energy, without changing its temperature, and only changing the temperature 1 degree, than aluminum could. Okay, so by that note, then, if I gave aluminum and water both the same amounts of energy, aluminum would change its temperature 4 times as much. okay, as water would. Right? So brick, 3.00, okay, concrete 2.9. You'll see most of the metals have pretty low specific heat capacities. Gold, okay, it's pretty low. It's very low actually. Human body, because we're mostly water, is quite high. Okay, ice actually has a different heat capacity than liquid water. This is a strange thing, but water is one of those weird things. Yeah, it's a polar molecule. Okay, it's solid form, liquid form, and gaseous form all have different heat capacities. Okay, which is rare. That's not the case for most things. Okay, but again, you can see the pattern here is that most metals, they have a very low heat capacity. Okay, whereas things that are more organic tend to have higher ones. Okay, alcohol, okay, they have pretty high heat capacities. Glycerin, okay, hydrogen has a very high heat capacity. Okay, 14.4. It's like by far the biggest thing. Okay, helium 5.25. Right, so you can see here, okay, quite a range of different heat capacities.
So water is H2O, is it just since hydrogen has such a high capacity question?
No, it has nothing to do with that. It's simply the nature of the chemical bonds and things like that. Yeah. All right, so you'll need that list because we're going to be doing a few problems to do with using this formula here in just a second. Okay, back to this here. All right, so the formula, like we said, okay, is E, standing for energy, okay, equals M times C times delta T. So M is the mass, okay, and it's in grams, not kilograms, but this is chemistry, okay. C is the specific heat capacity, so the numbers we just looked at, they're in joules per gram degree Celsius, and delta T is the change in temperature, okay, in degrees Celsius. Questions on the formula? Okay, it's going to be really easy for us to use. All right, so write this one down, because anytime I give you a new formula, I go through the way to solve each and every manipulation of it. Okay, so I'm going to go over this one here. I'll give you a second to get it written down, and then I'll go. Okay, so let's have a look at this one here. As always, we want to first write down our givens. Okay, so we want to know how much heat, so we're looking for energy, okay, is required to raise the temperature of 150 grams, so that's the mass, okay, of water from 5 to 85 degrees. So my temperature change is 80 degrees. All right, so I've got those three things. I'm looking for energy. So E equals M times C times delta T. So we'd have our 150 grams times 4.2 joules per gram degree Celsius times 80 degrees Celsius. So 150 times 4.2 times 80. All right, so that'll require 50,400 joules, but we're only looking at well, really one significant figure here, but let's say I said 5.0 just to make it 2. Okay, so we're looking at 5.0 times 10 to the 4 joules. Okay, everybody all right with that? All right, write this one down, and I'll walk through it here in a second. All right, so let's have a look at this one here. So what material, how am I going to find out what material something's made out of? What's that?
List.
Yeah, I got to get it off the list. So what part of the equation am I going to likely solve for? C, yeah. All right, so I've got 100 grams, so they tell me the mass. Okay, it's going to be exposed to 4,200 joules worth of energy, okay, and it's going to change its temperature from 12 to 62 degrees, so the temperature change is 50 degrees Celsius. All right, so E equals M times C times delta T. The only thing I don't have is C, so I'm going to divide both sides by M delta T. Okay, that'll leave me with C, so I'll have 4,200 joules divided by 100 grams times 50. That'll have to be bracketed, by the way, on the bottom. Okay, I think. Yes, it will. Okay, so we're going to have 4,200 divided by 5,000. All right. All right, so I'm looking at 0.84 here. So now I'm going to go back to my list of specific heat capacities. See if I can find something that's close to 0.84. Carbon dioxide is close to 0.84. But glass would seem to make more sense. It's exactly 0.84. Okay, so the material that this is probably glass.
Well, we got all this like the smart final.
You'll get whatever ones you need.
Okay.
Yeah. Okay, so all the ones I had, I think, on the formula sheet were water, ice, and steam. I think maybe I had gold on there too, or I just give it to you in the question if you need it. Okay. Try the next one. So this one is about as tricky as they can get, okay? Because you're actually asked to find the final temperature, not the temperature change. You have to find the temperature change in order to do it. But so again, we want to write down our givens here. We're looking for the final temperature, so I'm going to first find temperature change. Okay, I know that the initial temperature is 7 degrees Celsius. Okay, I also know the mass. Okay, it's 185 grams. I know that it's iron. Okay, so the specific heat capacity of iron is 0.460 joules per gram degree Celsius, and we are dealing with 200 joules worth of energy. Okay, so we got E equals mc delta T. So we solve for delta T by dividing both sides by m times C. Right, so we're going to have 200 joules divided by 185 times 0.46. Okay, so we're looking at a temperature change of 2.35 degrees. I'm looking for the final temperature, and I know the initial temperature is 7, so my final temperature is going to be 9.4, right? I think I only have 2 significant figures there, or do I have 3? I have 1, so 9 degrees Celsius would be my final temperature on this one. Okay. That's as tricky as they get, because you have to do one extra little mental calculation afterwards.
So hard.
Okay? Yeah, no, it's taxing. Really taxing. Okay, so I'm going to put those questions up, and once you guys working on those, obviously they're not terribly challenging, okay? But you can bet you'll see one on your unit exam, and it's part of our latent heat calculations that we'll get into possibly even today. Okay, we seem to be making good progress, so I'll see how we do with these. Now just kind of watch the way that these are set up. Like the first 5 all ask you to calculate C, and then the next 5 ask you to calculate energy. So maybe do like 1, 6, and what, just so you're doing a different type of one each time. I would suggest you probably want to call this up on your own phone, because I can't show very many of them on the space I have here.